In this video, I will talk about Probit and Logit models in R. Before you watch this video, please make sure that you have watched my other video called Probit and Logit Models. I have opened up the R script here for Probit and Logit Models. I have downloaded the data, MROZ.csv, and I have put it into my data directory here. And I have run this program, and here are the results in the console window, which is typically below here. So what we are going to talk today about, we are going to estimate Probit and Logit models, find the coefficients, then talk about predicted probabilities, marginal effects, pseudo R-squared, and percent correctly predicted. So let's first look into the data. So here we would have model of being in labor force for women. For this, we're going to read the data MROZ.csv into our data frame called MROZ. We will be selecting the following variables. In labor force, so basically this is a 0 or 1 variable whether or not women are working. Here is the non-wife income, which is going to be an independent variable, education, experience, the age of the woman, and the number of kids that are less than 6 years old. So once we select these variables from the data frame, we will use the structure, head 10, and stargazer to summarize the data. So this is how the data looks like. We have 553 observations, 6 variables, and these are the first 10 observations of the data set. So here in labor force, this is going to be our dependent variable, a 0, 1 variable. So the first 10 observations have ones because the woman is working, but there are also zeros in the data for women that are not working. Here's the non-wife income. This is the number of years of education, a number of years of experience, how old the woman is, and the number of kids that are under 6 in the house. And these are the descriptive statistics here for the variables. And we are seeing that the mean for the in labor force is 0.57. So here in the data set, 57% of the women are in labor force and the rest are not working. So if I ask you what is the unconditional probability of a woman working, it will be this 57%. So because we don't know any other information about the woman. So again, this is going to be the unconditional probability of women working. It will be 57%. Now, notice that this is a 0, 1 variable, the minimum being 0, the maximum 1. So this is the binary variable that we're going to be using as the dependent variable in the model. If we would like to use count to also summarize this variable in labor force, here we have the number of zeros is 325 and the number of ones is 428 in the data set. Okay, so now let's go ahead and estimate different models here. The first model that we're going to be estimating is the linear probability model. And the linear probability is basically, model is going to be basically a linear model, the dependent variable in labor force, and these are the independent variables. So we're going to be using OLS as the linear probability model, and let's call this LPM and then summarize this model. So this is what we see here. And these are the coefficients that we see for this model. So again, we're estimating in labor force regressed on all of these independent variables. And as we talked in the presentation for the lecture, we know that actually when we have a dependent variable 0, 1, but we ignore it and we actually use OLS estimation, it's basically not the best way to estimate this model. So what are better ways to estimate this model? And we can use the Probit and the Logit model for it. So how we call the Probit model, we're going to use GLM for this. And here for GLM, this is going to be the formula, same dependent variable and all of the independent variables. And here for family equals binomial and then link equals Probit. So we're going to be using the normal distribution to get to the Probit model. And here we are going to be reading datum MROZ. So to estimate, and of course we're going to be summarizing the results from this Probit model. So here for to run the logit model, everything is exactly the same except the link here would be equal to logit instead of probit. So that's how we're going to estimate a logit model, and here's the probit model. So the probit model uses the normal distribution, whereas the logit model uses the logistic distribution, and that's the difference between the two. But there are many good properties for the Probit and the Logit model over the linear probability model, which makes them preferable models to use. Okay, so when we estimate the Probit and the Logit models, this is what we see here. So this is the coefficients that we see estimated. And so these are the coefficients that we get here. And so the way to interpret these coefficients in a Probit model, for example, here for education, all we can say is that women that have higher education are more likely to be in the labor force. And we can also say that women who are older, so their age is higher, are less likely to be in the labor force. Even though, we see here specific numbers, we cannot interpret the magnitude of these coefficients. We can only say more likely or less likely here. And the reason for that is look at these. This is here the logit model. So this is where we use link equals logit for the logistic distribution. And here we see coefficient right here. This coefficient is a little bit different than the coefficient here. In fact, all of the coefficients in the logit model would be 1.6 times the coefficients in the Probit model. And it's simply because of the distribution that we're using. So this is why we cannot interpret the magnitude for these coefficients. So again, the only way to interpret this coefficient is to say women that have higher education are more likely to be in the labor force, and then women who are older are less likely to be in the labor force. That's all we can say coming from the coefficients here. Okay, so the next thing that we're going to be doing here is let's look at the predicted probabilities. So after we estimate these models, we actually could get the fitted values or the predicted probabilities. So how we do this in a linear model, of course, we're going to be using fitted for the linear probability model. So that was the linear probability model. We're going to use the fitted values here. So this is in labor force hat. And so that's what we're going to call this in labor force hat coming from the linear probability model. To get the probabilities for the Probit model, we're going to be using fitted for Probit. And here we're going to call these in labor force hat for Probit, and same for the logit. That's what we're going to call them in labor force logit, and that's going to be the fitted for logit. Okay, so now let's summarize these predicted values. So we're going to be using Stargazer, and let's summarize the in labor force, that's the actual value for the dependent variable y in labor force. And let's summarize the predicted probability coming from these models using Stargazer. And let's look at the first 5 observations here. And I have chosen, let's look at basically the observations from 601 to 605 in the data. So this is the observations from 601 and 605. So we're going to look on observations 1, 2, 3, 4, and 5, and then 601 to 605. So these are the descriptive statistics that we see here. So for the actual value in labor force, this is why we're getting the mean is 0.57. That's the mean that I showed you in the very beginning of this R script. And now as far as the predicted probabilities, here we have y hat coming from the three models. We actually have very, very similar numbers. So the averages are pretty much the same across the three models. So if we look at the actual predicted probabilities, this is what we see. So for the first five observations, from observations 1 through 5, these are the actual values. They happen to be 1 in the data. So these women here are working. The first 5 women in the data set are working. And what we see here for the predicted probabilities is that all of these numbers, if you look here in all of the models, are actually above zero point 0.5. So this is good because we know for sure that the actual value is 1. So these women are working. And so when we apply these models, the predicted probabilities, we're saying that they're actually more likely that they're working than them not working. So it's a very good thing that these predicted probabilities are above zero point 0.5. Now, if we look at these observations from 601 to 605, for them, women here are not working because in labor force is equal to 0. And here's what we're going to find as far as the predicted probabilities. So we already see one of the problems here is that we actually have a negative predicted probability. And that's a problem that we have with the linear probability model. The predicted probabilities are not going to be a number between 0 and 1. And you can also see this here, up here, when you have the predicted probabilities for the linear probability model. You see how the minimum is a negative number and the maximum is a number above 1? Well, that's not a good thing because we have these probabilities, predicted probabilities needs to be a number between 0 and 1, otherwise that does not make sense. But because it's not restrained, that's not going to be the case in the linear probability model. Notice that in the Probit and the Logit model, the smallest value and the largest values here, they are between 0 and 1. And so this is a good thing that a good property of the Probit and Logit models is that the predicted probability is a number between 0 and 1. So back here to this case, when we have the actual value being 0, these are the predicted probabilities that the three models are giving us. And so actually when the actual value is a 0, we want these predicted probabilities to be a low number. But for this observation right here, 604, you see that the predicted probability is a point 0.7. And that's actually problematic because now that predicted probability is a number above zero point 0.5. So we are actually predicting that this person here would be working because it's a high predicted probability, when in fact the actual value is that that person is not working. So here's where our models are going to make an incorrect prediction because we're predicting that the woman is going to work when in fact she's not working. So here, these are all correct predictions because the woman is working, the actual value is a 1, and the predicted probabilities are above zero point 0.5, so the model is also predicting that it's working. And same thing applies for here because the woman is not working and the predicted probability is less than zero point 0.5, except for this case. This is the incorrect prediction when the actual is 0 and the predicted value is a 1. So keep that in mind as we moved along this R script, because at the end we will talk about percent of the correct predictions that the models are doing. So now let's switch gears a little bit and talk about marginal effects. So how we do marginal effects is uh, for the linear probability model, if we use a summary from the model, the coefficients are actually the marginal effects in a linear model. So these are the coefficients here that we have, and they would be the marginal effects. These coefficients here in the linear probability model are the marginal effects. Now, there are two ways in which we can actually calculate marginal effects for the Probit and Logit model. So the first one is if we have the Probit model here, um, we are going to first need to have the mean of the independent variables. So here the mean, we would be using model.frame for the Probit model, and then map underscore df of mean, that's going to give us the mean of the independent variables. And so once we actually have these mean of the independent variables, then we can actually calculate the marginal effects at the mean for the Probit model. And to do that, we're going to be using margins. We're going to be giving here Probit, this is the results from the Probit model, and we're going to say at mean here. And this is going to basically give us marginal effects at the mean. So let's look at these marginal effects at the mean, and this is what we're going to see here. So marginal effects at the mean, these are the mean values as you could see for each of the variables, and these are the marginal effects at the mean right here. And so for the marginal effects of the means, now we can actually interpret these values. So how we're going to interpret them is, say, for example, here for education, we can say that for each additional year of education, women are actually 5.1% more likely to be in the labor force. Or another one is age. So for each year that women get older, they would be actually 2.2% less likely to be in the labor force. And so that's one advantage of using the marginal effects. We can interpret their magnitude. Another way is to calculate the average marginal effect. So for this, we're going to use margins and probits. So if we don't specify at mean, we're actually going to be getting the average marginal effect. And so here, these are the average marginal effects, and we see that these right here are a little bit different than these. So these are the average marginal effect, which means a marginal effect is calculated for each observation and then averaged across all of the observations, whereas marginal effects at the mean are calculated at these mean values for everyone. So here, how we're going to interpret these marginal effects, average marginal effects, is that for each year of additional of education, we see 4% more likely to be in the labor force, or for each year women are getting older, they're going to be 1.7% less likely to be in the labor force. So same thing for the logit model. Let's first look at the summary for the logit model. These are the coefficients. Again, we do not interpret the magnitude. We only interpret the direction for the coefficient. So here we just say more educated women are more likely to work, and we stop there. If we want to calculate magnitude, we need to calculate here marginal effects at the mean. So here we are going to be using margins. We're going to pick up the results logit that we have here at equals mean, so at the mean values. And let's look at the logit at means. This will be the marginal effects at the mean. And these are going to be the values here. So again, these are the average, the mean values for each of the independent variables, and these are the marginal effects at the mean for the logit model. So again, for each additional year of education, women are 5.4% more likely to be in the labor force, and for each additional year that women get older, they're 2.3% less likely to be in the labor force. As far as the average marginal effect, these are again the marginal effects calculated for each observation and then averaged across all of the observations. Here we have that again, women who are who have one more year of education are 4% more likely to be in the labor force, and women who are 1 year older are 1.7% percent less likely to be in the labor force. So notice now that unlike how the coefficients were very different between the Probit and the Logit model, the marginal effects between the Probit and the Logit model are actually amazingly similar. These marginal effects at the mean and the average marginal effect are a little bit more different from each other than if you compare the average marginal effect here for the Logit model and up here for the Probit model. They actually seem to be a bit more similar to each other. So again, when we use the marginal effects, that's a better practice because we can interpret also the magnitude of these marginal effects. Next thing that we're going to do is looking at pseudo R-squared. So again, we don't have R-squared like in a normal regression model, but we can actually create a similar concept here. So how we're going to do this, let's first estimate a Probit model that has all of the independent variables. So we're going to call this the unrestricted model. So if we summarize this Probit model, this is the results that we have here. And so from here, what we're going to be doing here is we're going to be ascribing this Probit model, we're going to be assigning to unrestricted dot model. And if we summarize it, that's basically going to be the same thing. We're just giving it a different name for the unrestricted model. Now, in order for us to get the log likelihood, we can actually use the log like for the log likelihood of the unrestricted model. So we're going to call this the log likelihood of the unrestricted model. And this number here would be minus 406. Now, if we have the Probit model for the restricted model that only has a constant, what we need to do is re-estimate the Probit model. And so we're going to use the GLM here. And dependent variable would be in labor force only regressed on a constant of 1. Notice there are no independent variables here. And here for binomial, we're going to be using link equals Probit. So here, this is a restricted model that has only a constant. And so if we summarize this model and we put it R model, if we summarize it, that's actually going to be, this log likelihood here is going to be 514. And here is minus 406. So basically, we started with 514 as the log likelihood, and this is if we have no independent variables. And as we're putting independent variables in there, that likelihood actually improved because it got to be a less negative number. So that's actually an improvement on the log likelihood. And so this is the idea that we're going to be using here to calculate the pseudo R-squared. What we're going to be looking at is what is the log likelihood for the unrestricted model divided by the log likelihood of the restricted model, and we're going to take 1 minus this expression. So in our case, this is a 0.21, and basically this is the pseudo R-squared. And so higher pseudo R-squared would mean that the model is going to have a better fit. It's going to be improving the log likelihood more. And so if we have a model here, unrestricted model, that is basically doing as good job as the restricted model here with no independent variables, this divided by this would be equal to 1, and that number is going to be close to 0 for pseudo R-squared. But if we have a model here that explains the data really, really well, this log likelihood here is going to be very much improved. So it's going to be a number that's closer to 0. Well, if this is closer to 0, this pseudo R-squared would tend to be closer to 1. And that's why this R-squared, pseudo R-squared, has similar interpretation to the R-squared before. But it's not based on sum of square residuals, but instead it's based on improving on the likelihood that we have here. Okay, so the last thing that we are going to do here is talk about percent correctly predicted. And in order for us to do that, we're going to get the fitted values from the Probit model. If they're greater than 0.5, we're basically going to call this a true prediction. Uh, and we're going to predict that as 1. And here we're going to convert this as numeric value, and then we're going to convert back as factor as we're going to make these predictions. And so now the actual data where we're going to have the actual value is going to come from the MROZ data frame, and this is going to be in labor force variable. And here we're going to convert this as factor because we wanna have this as factor, not as numeric. So this is going to be the actual data. And so now from the package caret, we're going to use the confusion matrix. And here we're going to give it the Probit predicted values. So here we have the predicted values. So basically, if we get a value that is for the predicted value that is greater than 0.5, we're going to give it a value of 1. Otherwise, we're going to give it a value of 0. So this is going to be the predicted values here. So we're going to be comparing these predicted values to the actual values. Positive equals 1 here. So that's going to be basically we're saying that the predictions here are being equal to 1. And so looking at the comparison here, these are now the predicted values that we have here. And let's look at what we call here the confusion matrix. So for the confusion matrix, this is what we see here. The reference value is the same as the actual value, and the prediction here is the same as these predicted values that we're talking about. So if the actual value is 0 and the prediction is a 0, we have 210 observations in the sample that were correctly predicted like that. On the other hand, if the actual value is a 1 and the prediction from the model is a 1, we have 346 observations like that. So if we sum up this value here, which is a correct prediction of 0 when the actual was 0, and this is also a correct prediction of 1 when the actual was 1. If we sum up these two values divided by the sum of all of them, this is this accuracy number that we see here. So what we are saying here is that the model, the Probit model, predicts 73% of the observations correctly, and the rest are incorrect predictions. So again, for 73% of the observations, if the actual was 0, the model predicted 0. If the actual was a 1, the model predicted 1. The rest are incorrect predictions. So here for this accuracy, or also called percent correctly predicted, we want a very high number, like above 70, 80%. We often see numbers even as high as 90% in empirical studies. So we can repeat the same thing for the Logit model. Same thing, we could actually get the predicted values for the Logit model, and then the confusion matrix would be the Logit dot predict. So these are the predicted values. So again, we're going to pick the fitted values from the Logit model. If they're above 0.5, we're going to call it a 1 as predicted value. If they're not, we're going to call this a 0. And we're going to predict we're going to compare the fitted values or the predicted values to the actual values. And basically, this is what we get for the Logit model here. For the Logit model, what we have is this is the actual values and the predictions. So here what we see is that we have one more observations here correctly predicted, but we have one less observations here correctly predicted. So if we sum up this plus this, we actually go and divide by all of the total number of observations here. We're going to actually happen to get the same percent correctly predicted, which is 0.73. That's usually not always the case that the Probit and the Logit model have exactly the same percent correctly predicted, but it so happened in our case. So in our case here, we have a relatively high number of percent correctly predicted, but still not but still, that's not an extremely high number in terms of values for percent correctly predicted for a Probit and Logit model. So again, what we talked today about was the coefficients and the marginal effects from the Probit and Logit model. We talked about pseudo R-squared, the predicted values, and percent correctly predicted. Thank you for watching.